Hi, and welcome to Special Relativity, the basics. Today we'll be using an analogy involving two trains to explain length contraction and time ordering. The first train is a relativistic train called the Lancaster locomotive. The second train is a non-relativistic train called standard steam engine. In fact, you might say they're trains of reference.
At non-relativistic speeds, as you would expect, a 100-metre train will perfectly fit within a 100-metre tunnel.
Einstein's theory of special relativity has quite a few strange implications. One of the most well-known ones is length contraction. Length contraction is the idea that the length of an object moving at relativistic speeds gets smaller along the object's dimension of motion. An observer at rest would see the moving object as shorter in length compared to what someone in the object's rest frame measures the length to be. This is because anything moving at light speed cannot have mass, and thus cannot have dimensions. So as things get closer to the speed of light, their dimensions get smaller. This relationship for length contraction is given by this equation, where L is the length as measured by the observer, L0 is the length measured in the object's rest frame, and beta is v over c, where v is the speed of the object and c is the speed of light.
So now let's take a look at the relativistic example. Let's imagine that you're an observer on the ground who's watching as this train enters the tunnel. The train is travelling at a speed close to the speed of light. Let's say in this example it's got a speed of 0.8 times the speed of light. So due to length contraction, the train becomes shorter. To calculate the length of this train from your frame of reference, we just need to use the length contraction formula, and plugging all these values in, this gives us a value of 60 metres for the length of the train. From your frame of reference, the tunnel is actually stationary, so it's not affected by length contraction and remains at 100 metres. This means that the 60-metre train will easily fit within the 100-metre tunnel. So now let's change the frame of reference. Let's imagine that you're actually standing stationary inside the train which is approaching the tunnel. So from this frame of reference, it's in fact the tunnel that's moving towards you and not the other way around. So in this case, it's the length of the tunnel that's affected by length contraction and not the length of the train. So applying that same length contraction formula to the tunnel, you can see here that that gives us a value of 60 metres for the length of the tunnel from this frame of reference. So whilst the length of the train still remains at 100 metres, this means that the entire length of the train can't fit within the length of this tunnel in this particular frame of reference.
So let's simplify the previous animation. We have two observers, the train and the tunnel, and three events. The front of the train entering the tunnel, event A, the front of the train reaching the exit, event B, and the back of the train reaching the entrance, event C. As we saw, due to length contraction, these events occur in different orders depending on which reference frame you are in. So which order of events is the correct order? Special relativity shows us that different observers in different reference frames can disagree on the order of events. This is known as the relativity of simultaneity. From something called the inverse Lorentz transformation, a general form for simultaneity of events can be found by considering two events at locations x-b and x-a and at tb and ta. The equations shown can be used to determine the order of events. This will be covered in more depth soon. So this means that the universe doesn't follow one linear timeline as we might expect. The order of events change depending on our frame of reference. Observers in various reference frames will experience events in different orders, or some may never experience them at all. However, we don't see this happen in day-to-day life, as these effects are negligible due to our slow, boring, non-relativistic speeds. We can still observe these effects happening at the quantum level and even in atomic clocks and GPS. I hope you have gained a better understanding of special relativity. Thank you for watching.